All right, so number 2, so we're going to draw a picture because it's actually really complicated. So you have a beam of light enters a tank of water at an angle of 30 degrees from the normal. Okay, so I'm going to draw a picture. So first, this is what happens. So you have air into water. And then here's my normal. And so it enters, so there's my incident, and so there's my theta I, which is 30 degrees, and it goes into water. Air has an N of 1.0003. Water has an N of 1.33. So since it has a higher N, that means that it's going to slow down. So if light slows down, it bends towards the normal. So it's going to bend towards, well, that's ugly. Okay, there we go, towards the normal. So then there's my theta R, and this is my refracted way, and I don't know my theta R. Okay? So that's the first sentence. After traveling through water, the light passes through glass at the bottom of the tank. Okay, so then what happens? So then it's going from water into glass. The N of water, that's where it's incident. So it's coming in at whatever angle this was. This is your theta I now. So this theta R is that one's theta I. And the N of water is still 1.33, and it says in the problem that the N of glass, which is now a refracted material, is 1.60. So we're going into a place with more optical density, which means it's going to slow down. So then this is going to bend even more towards the normal. So then there's my theta R, and I don't know that. Then it exits. It says then it exits the tank back into air. So then here's the third thing it does. I'm running out of space. There we go. So it goes from glass into air. So it's going from glass, where N equals 1.60. This is my incident, and this is my theta I, which is the same as my theta R that was right there. So that theta R now becomes this theta I. Air is refracted, so then that's 1.0003. So that, it's speeding up. So now it bends away from the normal. Okay, so then the questions, it says, what is the angle of light in the water? So they mean this one right here. So for part A, you're using the first thing and saying, okay, well, according to Snell's law, Ni sine theta I equals Nr sine theta R. So first, I need to divide both sides by Nr, so I can cancel it on that side. And then if I want theta R, I need to take the inverse sine of everything on this side. So then inverse sine of Ni sine theta I over Nr equals theta R. Okay, so A, you're going to do that, but only for the first situation. Then part B says, what is the angle of light in the glass? Okay, so then that's the second situation, and look, we want to know theta R again. We're going to use the exact same equation. But now my theta r that I just found for part A will be my theta I for part B. And then they want to know what is the angle of the exiting beam of light and air? It's a trick question. It started in air, and it's going to end in air. They should be exactly the same. If all you changed was the medium, and you didn't change the angle of incidence that it first went into air, it should be exactly the same. You can test it out mathematically and see if you get the same number, whatever you want. So I've set up number 2 for you. I'm not going to do it, but I've set it up. You should be able to finish it. Okay? Okay, so now we're going to do number 7 on the same page. All right, so a student holds a 1 centimeter tall candle. So the height of the object is this super tiny candle, because 1 centimeter is really small. I don't know who made up this question, but whatever. So an almost burned out candle, okay? They hold that candle 50 centimeters away from a convex lens. So the distance of the object is 50 centimeters. Then it says the image is formed 12.5 centimeters in front of the lens. So that means it's positive because it's where it's on the other side where the light converges. So that's going to be a positive number. So that's DI is positive 12.5 centimeters. And for part A, we want to know what is the focal length. And for part B, we want to know the height of the image. And then for part C, they want us to classify the image. So for the focal point, I would use the thin lens equation, but I would rearrange it. So I would say F equals 1 over DI plus 1 over DO, and then invert it. So then that would be 1 over 12.5 plus 1 over 50 inverted. Okay, so 1 over 12.5 plus 1 over 50, and then invert. And you get 10. Okay, so F is 10 centimeters. Okay. So then part B, you want to find HI. I would use the magnification equation. So the height of the image over the height of the object equals negative of the distance of the image over the distance of the object. I'm looking for HI, so I'm going to multiply both sides by HO. Just some simple algebra 1. So then that's negative of 12.5 times 1 over 50. So I get negative 0.25 centimeters. Okay. So now we have to classify the image. Well, my HI is negative. If my HI is negative, I know it's going to be inverted. If it's inverted, it must be real. So I know that this image is real and inverted. And then I have to figure out if it's magnified or reduced. Don't have to calculate M. I just look at the HO compared to the HI. The HO is 1 centimeter. The HI is 1/4 of a centimeter. So since the image is significantly smaller than the actual object, this is reduced. So I got most of that. I got 2 of these just from the sign on the HI, and I got how big it is just by comparing the height of the object and the image, and that's all.